Good morning, student. Today I'm going to discuss about parallaxes, the method by which distance of the stars can be measured. As you know, the stars are very far away from us. Therefore, to use the method of parallaxes to measure their distance, the baseline has to be very extended. But this is obtained by measuring the angle of the stars in two different locations during the revolution of Earth around the Sun. That means the diameter of the orbit of the Earth becomes the baseline. With this huge baseline, many stars show very small parallaxes, though modern telescopes have measured parallaxes of millions of stars. We'll discuss this later. So let us first understand what is the parallax method. Say this is the orbit of the Earth. Sun is situated here. Now Earth is here one time. Say one star is there. So we are measuring its direction. And after 6 months, it will be here. So this distance will be 2r, r being the radius of the orbit of the Earth. Now, the angle of appearance of the star, this angle is parallax. If we join the line with the sun, then this will be theta, and this will also be theta, so that this angle will be twice of theta. Now, there are many things, minute things here, because as you know, if you observe a star over your head, that means near the zenith, then due to refraction of light in the atmosphere, Earth's atmosphere, its deviation will be small. But if you observe the star near the horizon, then your due to diffraction of the light, the line of sight of the star will be different from its original direction. And it can be shown that this angle of deviation due to diffraction may be larger than the angle of parallaxes. So for that thing, generally what is done, a reference star which is much more distant is taken, and with respect to that star, nearby star, other stars, parallaxes of the other stars are measured. So this way, the deviation due to refraction of the atmosphere can be eliminated. So we will not go detail into it. It will be needed for higher study. For the time being, we are considering the parallaxes due to the huge baseline of Earth's orbit. Now, you know, if this is the distance, capital D is the distance, you know this is R. This R equals to, we have taken it as 1 astronomical unit. R is 1 astronomical unit. Theta is the angle, then we can say that 2R by D, it will be equals to twice of theta. So this cancel out. So D will be equals to R by theta. Now if R is 1 astronomical unit by theta, in where theta is in radians. Where theta in radians. So this simple method can be used to measure the distances of stars. For example, this angle is called angle of parallaxes. This angle is called angle of parallax. Now, you can understand that the closer a star or an object in the sky is, the larger will be its parallax. And if it is far distant away, they may not show parallax. In fact, if we measure parallaxes of the stars in the night sky from Earth-based telescopes, then most of the stars do not show parallax. However, in modern times, telescopes are fitted in the space above the Earth's atmosphere, and that these telescopes can measure parallax angle very accurately. We'll come to that later. For the time being, take as an example, Proxima Centauri is a star. Proxima Centauri. Proxima Centauri is a star with angle of parallax theta equals to 0.7685 arc second. Arc second is the angle. Means the angle is measured in degree radian second, arc second. So this is 0.7685 second. Now we have to convert it into radians. We convert it into radians, then this will be 0.7685. How much radian? How much radian? It will be calculated as 206.265 radians. You know, 1 second, 60 second equal to 1 minute, 1 minute equal to 60 minute equal to 1 hour, and 60 second equal to 1 degree, 60 degree equal to 1 degree equals to 60 second, 60 second equal to 1 minute, or 60 minute equal to 1 degree, and 1 degree equal to how much radian? You know, 180 degree equal to pi radian, so 1 degree equals to pi by 180 degree radian. And if you perform this thing, then this will be like this. Therefore, the distance d of the Proxima Centauri, would be 1 AU by this distance, 0.7685 into, this will come up 206.265 AU. This will come out to be 268,399.48 AU. I'm sorry, it's not visible. AU. And if we convert it to light years, we know 1 AU equals to 1.496 into 10 to the power 11 meter, and 1 light year equals to the light, that distance light travels in 1 year is 9 into 461 into 10 to the power 15 meter. So accordingly, 1 light year equals to 1 AU equals to, if we divide this by this, then it comes out to be this thing. So in light years, 268,399.48 by We do this thing, then it will be 6.234 into 10 to the power 24 light years. Equals to 4.3 light years. So this is the distance, Proxima Centauri. It is very near to us. In fact, we know many of the stars are far distant away from this. Now, a telescope known as Hipparchus in 1989 to 1993 measured 1,18,200 star parallaxes. That is huge data. And recently, Gaia telescope, which is launched by European Space Agency, measured 1.3 billion star parallaxes. Gaia telescope, which is installed in 2012. Gaia telescope of European Space Agency, 1.3 billion stars. Star parallaxes has been estimated with an accuracy of 25 microseconds. Means 25 into 10 to the power minus 6 microseconds. This corresponds to distance of 1,000 or million, 40,000, I guess 40,000 light years or something like that. So tremendous accuracy that Gaia telescope has. Now, parsec is another useful unit for distance. You should know it. Astronomers are using parsec. Parsec, or abbreviated as PC, is a distance. It is defined as the distance at which the distance of or length of one AU subtends an angle of 1 degree. That means 1 PC would be equals to 1 AU by 1 second. 1 second. Parsec is the distance at which a 1 AU distance will subtend an angle of 1 second. Now, if we know 1 second equal to how much radians, then this comes out to be 206,265 AU, and which comes out to be 3.19 light year. So this is the distance nowadays is used by the astronomers, and which is parsec is the distance, and which is equivalent to 3.19 light years. So this is the angle of parallaxes by which distance of the stars, most of the stars, have been measured. Now let us move on to the next topic, which is the brightness, luminosity and magnitude of stars. Brightness of a star can be determined from the how we'll measure brightness. Right now it can be measured by the amount of energy received per unit surface, per unit time. That means power per unit area. So this is called the flux density or radiant flux density. But our eye is not uniformly sensitive to all the wavelengths. In fact, our eye is sensitive to visible light, but not all the lights are equally sensitive to our eye. For example, red light, green light, blue light, yellow light, among all these lights, blue light is more sensitive to our eye. And the instruments, moreover, our eye is not sensitive to ultraviolet or infrared radiation. But we know from sun or from the other stars, these rays, ultraviolet or infrared rays, are also coming. And the instrument that we use generally use a band, means different wavelength range is detected. So it is sorry, it will be very useful to define flux density in a specific frequency range, and we call this specific flux density. So now let us move on to the flux density. Flux density, F, is amount of energy received per unit area per unit time. Now du by dt is the power, so its unit will be, or you can say dp by dA, where p is the power. This is energy, this is power, and its unit will be what? Its unit will be watt per meter square. SI unit will be watt per meter square, or simply we write W by meter square. But as I have discussed, as I have told you, that the different instruments as well as our eye is not sensitive to all the frequency ranges. So we have to define specific flux density. Specific flux density, F nu equals to dE by dA dt du. That means for unit frequency range, and its its unit would be watt per meter square per hertz. This will be its unit. Now, what is the very large unit compared to the energy or the power of the stars that we receive in Earth? So, a small unit called Jansky is used. Jansky, 1 Jansky equals to 10 to the power minus 26 watt per meter square per hertz. So generally, specific flux density is denoted in the unit of Jansky, which is a very small unit, because generally the power received on Earth of the stars is very small. Now luminosity, let us come to the luminosity. You know what is luminosity? I'm sorry. Luminosity is defined as the total energy emitted by a star per second. This is called luminosity. The more luminous of a body is a body, the more bright it would be. Now, what is the relation between this luminosity and flux density? As we have discussed in terms of flux density, there are two types of flux density. One is flux density for all wavelength range, for all frequency ranges, and another is specific flux density. So luminosity can be like that. One is the specific luminosity, that is luminosity for a fixed frequency, and the total luminosity. And this total luminosity is also called luminosity. Total is called bolometric luminosity. Bolometric luminosity. Bolometric luminosity is the total luminosity, means considering all the frequency range. For example, the bolometric flux density F equals to 1360 watt per meter square in case of sun. In case of sun, the bolometric luminosity, that means the energy received, power received per unit area, 3.1360 watt per meter square. This is known as solar constant also. Solar constant. Now, what is the relation between luminosity? It is called luminosity is denoted by L. What is the relation between L and F? Luminosity and flux density. This is a simple relation, as you know. L F equals to L by 4 pi d square, where d is the distance of the star under consideration. So F equal to L by 4 pi d square. And if we consider specific luminosity, then F nu will be equals to L nu by 4 pi d square. 4 pi d square. So there is a simple relation between luminosity and brightness. So if you know the brightness, the brightness, that means the energy received per unit time per unit area, then we can calculate the luminosity provided we know the distance of the stars. And this way we can measure, we can estimate the type of a star, its luminosity, and compare it with the luminosity of the sun. Now, for nebulas and galaxies, these are extended bodies. So, in order to measure their brightness, another quantity for galaxies and nebulas, another quantity of interest is the solid angle d omega. D omega is needed. In that case, flux density is defined per unit solid angle. d dt d nu d omega cos theta, where theta is the angle between the solid angle d omega and the area dA. This angle is theta. Angle between solid angle d omega and the area dA, over which the flux density is measured. Generally, flux density is measured by the photographic plate, and the area of the photographic plate dA will be the area, and the angle of the line of sight with the solid angle of the galaxy is the theta. So in case of galaxies or nebulas, this luminosity, this has to be defined. Now, what will be the energy density of radiation? Now, energy density is the amount of radiation per unit volume. You see, E is the energy density. Then energy density would be 4 pi by C F, where F is the flux density, then U would be 4 pi C by F. Now, how we will measure brightness? Generally, brightness is not measured with the measuring of energy. Rather, it is compared with a reference point. That means, if we know the brightness of a star, then we can compare the brightness of other star with respect to that star. So we don't have to measure the energy each time. So for that case, we define another quantity which is called magnitude of a star. And what is that? Magnitude of a star, which is the measure of brightness of a star, is defined as magnitude of a star, magnitude m equals to minus 2.5 log f by f0, where f0 is the luminosity of a reference star, which is taken as Vega. Vega is a moderately bright star in the northern sky, and its magnitude is taken to be how much? It will be 0. So magnitude of Vega, it will be 0. It is taken as 0, and with respect to which other stars are, magnitude of the other stars are measured. Now we can question why this formula is there. There are two apparent reasons. One reason is that our eye is not sensitive to brightness in a linear scale. It is sensitive to a logarithmic scale. That means a brightness factor of 10 is to 100 is to 1000 would appear to our eye as 1 is to 2 is to 3. Is that clear? That's how our eye perceives or measures the brightness of star. So in terms of energy density, if the difference is very large, huge, but in terms of brightness that measured by our eye is very small. That's why log scale is used. And why 2.5? To make the quantities m to a perceptible or near to a whole number. So in this scale, the magnitude of Vega would be 0, and the stars brighter than Vega, will have a negative magnitude, and the stars fainter than Vega, these are brighter and these are fainter, the magnitude would be positive magnitude. So in the scale of magnitudes, it is positive magnitude denotes less brightness and negative magnitude denotes higher brightness. So in this scale, the brightest star that we see in the night sky, Sirius, Sirius is a star in the constellation of Orion, which is in fact a binary star, means a double star. So when we say about the brightness of Sirius, we are taking both the stars. So it is minus 1.46. That means it is much brighter than Vega. The brightness of Moon, magnitude of Moon is minus 12.5, and magnitude of Sun is minus 26.5. So in this scale, the brightness is not, the magnitudes are not too much different, but if you calculate their ratio of flux densities, that means energy received or power received per unit area, then it will be that this ratio will be very large. We are coming to that. Now, one of the important thing is one magnitude difference is equivalent to 2.512 brightness factor. This can be proved this way. We have defined m to be this. So m equals to minus 2.5 log f by f0. Let us m minus 1. And what will be this? Minus 2.5 log f m by f0 plus 2.5 log f m minus 1 by f0. So it would be minus 2.5 log this minus this. So it would be fm by fm minus 1. Now if this difference is 1, then fm by fm minus 1 would be equals to 1 by 2.5. So fm minus 1 would be equals to log minus 1 would be equals to fm into 10 to the power 4, 0.4, 0.4 approximately to 2.5. You can calculate it with your own hand, and I will suggest you to do this calculation. So one magnitude difference is equivalent to 2.51 to brightness factor. Now I am giving you a homework. Please compare the ratio of the brightness F Sirius is to F moon is to F sun. Compare it. Next, we will move on to different terms related to the magnitudes. Different magnitude field magnitude scales are used. Generally, for visible light, we say MV denotes magnitude for visible light. Visible light. Generally, the peak of which visible light sensitivity of eye is taken as sensitivity eye is highest in the blue-green range. Generally, wavelength 550 nanometer is taken as the peak of the sensitivity of visible light. Then MPG, it is photographic magnitude. It is called photographic magnitude. Photographic magnitude. Photographic plate. So it will be visible plus infrared plus ultraviolet. Ultraviolet. And another is Embolo. You know already, magnitude for all wavelengths. For all wavelengths. Now this can be measured. This can be perceived by our filter. This can be measured, but we cannot measure this. We cannot measure this thing. We can't measure because there is no instrument. There is no instrument by which all the wavelengths can be detected simultaneously. Now what should I do? But there is a way. What is the way out? If we know the bolometric correction, what is called BC. BC is called bolometric correction. Bolometric bolometric correction, then M bolo can be taken as visible minus BC. Generally, for solar type stars or in case of sun, the bolometric correction is 0. This is equals to 0 for sun, or more precisely F5 stars. Spectral class of F5 stars. We will go detail in this spectral classification later one, but now you can what we can say is that the bolometric correction, though it cannot be measured, it can be estimated if you know the magnitude for visual range or in the photographic range. In the next class, we will discuss about filters and absolute magnitude. Why absolute magnitude is needed? You know, the stars that we see in the night sky are not equidistant. They are far apart. Some are near and some are very distant. But in case of magnitude, which is called apparent magnitude, the magnitude that we discussed, they are called apparent magnitude because we are not considering the distance in it. So, to compare the luminosities, we have to know the distance. But if you know the absolute magnitudes, means if you know the magnitude of the star or the luminosity of the star, then we can measure its distance. In the next class, we will consider these things. Also, other factors are there. There are filters and different color indexes are there. We will discuss in the next class.